Hi guys, let's talk a little more about work. So far, let's see. We've looked at some simple definitions. We've been working with the fact that work is F dot D, the force dot the displacement, and we looked at also that we could express this definition as FD cosine theta, where if we imagine this as the force as one vector and the displacement as another, this theta would be the angle between them. And we looked at some both simple examples as well as some examples that were more complicated and depended on using the I hat, j hat, k hat notation. So what I want to talk to you about now is basically what if the force is not constant? So what if F varies? So let me give you an example to sort of compare. One of the simple examples we looked at was, suppose you have like a box or something and you pull it and you scoot it some distance. And when we had talked about this example, we'd always sort of assumed that there was nothing changing with the force. So one way to think of this computing the work in this situation, remember this was F d cosine theta, is we could do this, we could think of this graphically as a function of x, and this would be let's move this up here. This would be F cosine theta, and so since this force is constant, this would look like a rectangular region, the work. And this was all because the force wasn't changing. So you can imagine a different scenario here where maybe we're pulling our box. Initially the force is quite small, and then maybe we, at some point we really pull on it much harder, and then maybe later, the force is again. So this is all the same box. Sorry, let me try and draw this nice and evenly. And then maybe later we pull it, with a small force again. So we could, and if we were to look at the total displacement, that would be again this d. Now in this situation, when we go to look at the work, our graph of the force as a function of x would not just be constant, but it started small and it got large and then it got small again. So it would look something like this. And in this case, so we don't have the cosine because we're just pulling on it at an angle of 0. But the work, instead of it just being a rectangle, the work is going to become an integral. And integrating is how we deal with the fact that the force wasn't constant. Technically, we're doing the same thing when the force is constant, but the integral is just a rectangle. If the force is varying, we have to use more complicated mathematical tools. Okay. And, technically the angle could also be changing, but we're just limiting our discussion now for the case that the angle of D, or for the case that the displacement and the force are pointed in the same direction. So let me just make a note here. I'm just going to put F and D are parallel, in other words. So one of the, probably the most common force that we would deal with in this way that changes with X or with displacement is one that we've encountered. We encountered it in lab, and that is the spring force. So common example, spring force. So if you remember, the force due to a spring is given by negative kx, where this k is called the spring constant. And recall, it had units of newtons per meter. And this negative sign indicates that it pulls against you. So we can find the work done by the spring force by integrating this. And I'm just going to call it from 0 to some capital X final. Oh, and let's of course draw ourselves a picture. So we have a spring, we have an object attached to the spring. And if you pull on this, we know that the spring force is going to pull back. And so if we moved this guy, our spring would stretch. The spring force would be larger. Our pulling force would also have to be larger. And this would correspond to a displacement like that. So the spring force and our displacement are actually in opposite directions. So the spring force is like this. The displacement is like this. Oops. So when we go to evaluate this integral, what would this look like? Well, we would have that the work, the integral of something proportional to x would be x squared over 2, evaluated from 0 to capital X final. And when we put in our limits, we would find that this is negative k x final squared over 2 minus 0 squared, so there would be a 0 from our lower limit. And I should clarify here, x equals 0 is the equilibrium position. So where the block and spring starts from, where it's at rest. And you can think of this graphically too, actually. If we give ourselves a picture of the spring force as a function of x, notice that, remember, the spring force is negative kx, so it would be a line, just like we talked about in lab. And I've made this positive just so we can think about it in terms of an area, even though there's that negative sign there, but you get the idea. So at x final, remember, this spring force is negative kx. So if you wanted to find the area in this situation, it's the area of a triangle. So it would actually be negative kx final would be this position, right? Times x final. So that would give you the area of the whole rectangle, times 1/2 because it's a triangle. So notice this would be negative k x final squared over 2. So it's a graphical way of showing the same result, the work done by the spring. And we can verify, or it should be logical that the work is negative because the force and the displacement are in opposite directions. So when you look at the dot product between them, that would give you a cosine of 180 degrees, which would give you a factor of -1. So let me just specify here. This is the work that's done by the spring. The other work that we can talk about is, the work that you've done by pulling on it. Now, in that case, your force pulling and the displacement are in the same direction, although those are the same size, right? Because if you look at the sum of the forces in x, you would have the pulling force minus the spring force. And just like in lab, if you're just pulling on it and it's not accelerating, this would equal 0. So these forces have the same magnitude, but they're in opposite directions. And so the work that you would do, let's call it just the work of pulling, would equal positive kx final over 2. And like I said, this kind of makes sense because the displacement and the pulling force are in the same direction. So while you are doing positive work to stretch the spring is doing negative work. So this example of a spring is probably the most common example of a situation where you have a varying force. And let me show you now a couple example problems. So that's what we're going to do. Next is example problems. So the first example that I want to show you is similar to this. It's a spring problem. So here's the question. The force needed to hold a particular spring compressed an amount x from its normal length is given by F equals kx plus ax cubed plus bx to the fourth. How much work must be done to compress it by an amount capital X, starting from x equals 0? So this is a variation on the spring problem that we just talked about, except our spring is a little more complicated. So we have this relationship. And instead of stretching the spring, we're compressing it. And so let's draw ourselves our little cartoon here. We have spring, and notice that it says the force needed to hold a particular spring compressed. So that is this force. And if we are compressing it, then not only is the force pointing that direction, but the displacement in it is as well. So if we look at where the displacement is, looks like this. So in other words, the force and is parallel to the displacement. So what this tells us is that this work will be positive. So we're gonna integrate this. So since the force isn't constant, we need to do an integral from 0 to x. Let me call actually x. I'm just going to call this x final, just so we can more easily distinguish it from the variable that we're integrating over, lowercase x. So the force expression that we have to work with, kx plus ax cubed plus bx to the fourth. And we're integrating that from 0 to xf. So what do we get? This we would have kx squared over 2 plus ax to the fourth over 4 plus bx to the fifth over 5, evaluated from 0 to xf. Oh, and I should say, this would correspond to x equals 0, the equilibrium position, and this would correspond to xf. Okay, and so when we put in our limits, this would look like k xf squared over 2 plus a xf to the fourth over 4 plus b to the fifth over 5. And, we would subtract off then 0 plus 0 plus 0, since we're starting from that equilibrium position of x equals 0. So this would be the work. It's positive, as we mentioned, because F and D are pointed in the same direction. And this gives you an idea. So let me just make a note there. This is since both of these point in the same direction. And this is a good example of sort of the analytical type of problem that you might be asked to do, where you need to be able to integrate a simple function. Things like polynomials like this, you should be able to do. So this is one kind of problem. Let me show you a totally different style of problem, but that gets at the same idea of working with varying forces. Oh, actually, before I do that, one other thing I would mention is, this is the force to compress. The spring, though, is pushing back the other direction. So you could also talk about this as being the work that the spring is doing is negative. Let me just make a note here. The work done by the spring is negative because F and D are anti-parallel. So because, the force of the spring is this way, the force of the spring is this way, but the displacement is this way. So just a side note. So let me show you a different kind of problem. And I think there's a problem like this in your homework as well. So this is a graphical style problem. So another way to think about forces that vary is to consider the situation graphically. So this is a graph that shows you how the magnitude of the force as a function of x. And let's read the question. So the force on a particle acting along the x-axis varies as shown. Determine the work done by this force to move the particle along the axis, the x-axis, from 0 to 10 and from x equals 0 to x equals 15. So to solve this kind of problem, what you actually need to do is to find the integral, but what that amounts to is finding the area under the curve. So this is probably a definition of an integral that you're familiar with. And this, so in the language of our integral, what that would look like is you're integrating f of x from 0 to 10. And what would that be? Well, we need to figure out a way to break this thing up so we can figure out its area. So I'm going to draw some straight lines. You can see that we could find this triangle, this rectangle, and then this triangle to find the total. So what would that look like? Well, this would be something like 3 times 400 times a factor of 1/2, because we're just talking about that triangle, plus 4 times 400 plus 3 times 400 times another factor of 1/2. So let me just use that. And what would this look like? So this would be, basically 7 times 400. This would be 2,800 joules. So that would be the work from 10 to from 0 to 10. And if we want to find the work from 0 to 15, we're going to need to find the area of this region as well. Notice this is negative. So up here, the force is positive and the displacement is positive. So in other words, this would be positive work because, but down here, the force is negative while the displacement is positive. So this will be negative work. So let's find this area from 10 to 15. So what would that be? Well, this is a little bit smaller of a region. Kind of tough to draw. Let's see here. This would look like looks like 200 times basically 1.5 times 1.5, or a factor of 1/2. That would be this little triangle here. And then we would add to that something that looks like about 200 times 2, and plus, another triangle here, which would have that same area. Oh, and I should say, talking about this negative sign, really these pieces are all negative. Negative 200. So when we add that up, this is basically, negative 200 times 2 plus negative 200 times 3/2. This would add up to about negative 700 joules. And as a result, the work from 0 to 15 then would equal 2,800 minus 700. So this would be 2,100 joules. So hopefully this gives you an example of another kind of problem that you can solve, and that's with varying forces, but a graphical style problem.